12.8 is just going to continue the stuff we did at the end of 12.7. So the whole point of power series is that we want them to represent functions, but at the beginning of 12.7 we just kind of introduced them as their own objects and went from there. So in this section we're going to use a couple basic series and then try to find some new series based off of those. So I'll just notice, it was 30 seconds ago, but I'll say it this way. Recall that e to the x could be represented by the power series and then what did we also say last time? What was the radius of convergence for this series? I guess it's still on the board over here. It was infinite, right? And so this is true for all numbers. And so this is our first example of something that represents another function. And so with this, we can build some new power series pretty easily. So if somebody said, find me a power series for e to the 2x. Okay? E to any x, right, is x to the n over n factorial plus blah, blah, blah. So if I want e to the 2x, what do I do? I just replace that x with 2x. Does that make sense? So I get x to the, or 2x to the n over n factorial. Make sense? And again, if I wanted to write that out, it would be 1 plus 2x plus 2x squared over 2 factorial, so on. And notice, right, this holds for this holds for every x, and so no matter what my 2x was, this will still make sense. And usually we don't want to leave it this way. We'll usually write it like this, which is 2 times x to the n is 2 to the n x to the n over n factorial. But that point is that just some simple algebra plugging in 2x gives us a new power series. And even another one. Let's do this. E to the x squared. Follow the same logic we just did on the other one. See if you can come up with a series for e to the x squared. So what did we end up with?
X equal to the power of
X squared to the n. Right, you're just replacing the x inside that x to the n. And x to the 2 to the n is x to the 2n over n factorial. That make sense? So that looks like that one we saw earlier that had a 2n power, right? So those are where those kind of series can really naturally arise. And so that's still a power series, but it's just going to skip all these other terms. And let me just notice, when you plug in 1, you'll get 1. Then you'll get x squared. When you plug in 0, you'll get 1. When you plug in 1, you'll get x squared and 1, right? And then you'll get x to the 4th over 2 factorial, x to the 6th over 3 factorial, and so on. And again, it didn't matter what x we plugged into the equation for e to the x, so this is well defined for all x. So we'll write that at the end. So when we write out these power series, we'll write this form. Sometimes we'll write this. You don't always have to do that, but we always at the end want to say this is valid for any x in this interval. Okay, we'll fix that. All right, so let's get to the real bulk of what this section is. There's another series that we're used to, which is, well, let me just write this out. am I going to write? This is the series just x to the n, right? What kind of series is this? If I replace the x with an r, what series was this? It's a geometric series, right? And so it's a geometric series with a equal to 1 and r equal to the x, right? What was the sum of a geometric series?
It had to be less than 1.
Right, so that's what I was going to come to next, but it was a, in this case, 1 over 1 minus r, right, or 1 minus x, and then the absolute value of x had to be less than 1, and so I'm going to write it in the interval form. This will be valid on this interval. Does that make sense? So here's our function, and we can represent it by that power series. Does that make sense? And so that all comes from what we've done before. We've already seen that this is a valid way to represent this, but it only is defined when we stay inside of here, right? So now let's try to build some new series like we did with e to the x using that series. And so to build these new series, we're going to do algebra, and then we're going to use derivatives and integrals. But let's just write it out one more time. 1 over 1 minus x is 1 plus x. And you're going to want to be comfortable writing your power series sort of in both forms, right? The sort of expanded form like this and the summation form. And we'll go from -1 to 1. So, find a series to represent, and then each of the following. So let's just do 1 over 1 plus x. So for all of these, probably almost for the vast majority of the rest of the class, I'm just going to be using this formula here. Slight tweaks on it. So 1 over 1 plus x. How does that relate to 1 over 1 minus x? It's 1 over 1 minus negative x. Does that make sense? So if I have a formula for 1 over 1 minus any x, I can replace it with negative x and I'll get a new series. And notice, right, this series is fine as long as the absolute value of x is less than 1. The absolute value of negative x will be less than 1 exactly at the same time, right? So it'll be a series that works for the same set of x's. So all you do is replace your x's with negative x. So what do we get? 1 minus x, negative x squared, which is
X squared.
plus x squared, minus x cubed is negative x cubed, right? They'll just alternate plus and minus like that. Okay? And if we wrote that in terms of a sum, let me just do it up above. It's negative x to the n, right? But that's negative 1 to the n, x to the n. And again, it's the same interval of convergence, right? Because you're just replacing x with negative x, so if you take absolute value, you get it. All right, any questions so far? Okay, so let's try a couple more here. One over 1 minus 2x. And actually, I'll write a couple up here. Just kind of play around with them. Again, these are all just going to be simple algebraic manipulations of this series that we've already been working with. Let's do 1 over 1 plus x squared, and then 3 minus x. All right, take a minute. See if you can come up with series for any of these. Alright, so let's try this first one. Again, right, we're coming back up to this series, and so what are we doing with the x's? We're taking x and replacing it with 2x, right? So we use this series, but put 2x in instead of x. So what do we get? 1 plus 2x plus 2x squared. Does that make sense? You're just substituting those in at each stage. Plus 2x cubed, and so on. And then if you do it in terms of this sum, it's just 2x to the end. Now, I suppose this works okay, but usually when we write these, we want to have sort of x to a power by itself. And so if we do that, it's 1 plus 2 and then x, 2 squared x squared, right? Just nothing too fancy here. X cubed and then so on. And then this form, right, 2 to the n, x to the n. So that's how I'd like to see those written. Now we've ignored the bounds here. Do I still go from -1 to 1? -1/2 to 1/2. Now if you don't see that, all you have to do up here is think, right? This works when the absolute value of x is less than 1, right? And down here, what did we plug in for x? 2x, right? And so we need that absolute value of 2x to be less than 1, just like we had here. In other words, that has to be less than 1/2, right? So if you don't see it, that's one way to sort of come up with it. And again, for now on these power series, we're not going to worry about the endpoints. We're not worrying if something converges at an endpoint. We're just looking at these open intervals and everything will stay nice in between them. Okay. How about this guy? And I will say, right, over here we had, I said memorize, I didn't say, but you should memorize this series, right? This should be a series you know. And it's probably worth knowing this series as well, the 1/1 plus x. Again, you can come up with it in just a second if you need to, so if you forget it, not a big deal. But it shows up often enough that it's worth knowing. So 1/1 minus x, just the sum of the powers of x. 1/1 plus x, just the alternating sum of those powers, right? So if we see this, 1 plus something, we can just use the alternating form instead, right? If you had to, you could have also made it 1/1 minus negative x squared and just use the original form with negative x squared. I like to think of doing it sort of piece by piece, where I'm using the one we've already done, and then I'm going to just tweak it even further. So I'm going to take the series we already have and replace the x's with x squared, so it's 1 minus x squared plus,
X
X squared.
good, minus,
X squared third.
cubed, good, plus,
X squared
fourth.
fourth.
And you could go further, but I think it's almost even better than to just do this. The sum from 0 to infinity, -1 to the n, and again, I replace the x with x squared, right? And so even if you just did this, you get the sum, -1 to the n, x to the 2n. Okay? And then what's the values that that makes sense on? So I was plugging x squared in for x. I know the absolute value of x had to be less than 1, and so a square is less than 1 exactly when the original was less than 1, right? And so this is the same bounds. Just be careful if there's something different going on. Okay, so this is our last one in this form. So you should probably do a little bit of algebra here first, right? Our formula is for 1 over 1 minus something. And so if you have a 3 here, you can just force it out. If I just pull a 1/3 out, then what am I left with? Right? I pull a 1/3 out from here.
It's just 1 minus x over 3.
Over 3. Does that make sense? And now we can just use the same form, or the same method we just used, right? So this is the 1/3 will sit there, and then what's the series for 1 over 1 minus x over 3? You just use the original 1 over 1 minus x formula with x minus, or x over 3 in instead, right? So it'll become 1 plus x over 3 plus x over 3 squared, x over 3 cubed, and so on. Does that make sense? Now, you might clean this one up, because this one would be what, 1/3 plus x over
3.
over 3 times the other, where that 1/3 on the outside comes in and multiplies by everything. X over 9, x squared over
27.
27, cubed over
81.
81, and so on, right? And if we thought of this in sum form, right, it's just x over 3 to the n, and then there was that 1/3 out in front of everything, right? So you get that. And so if you break this up, 1/3 x to the n over 3 to the n. If I multiply that 1/3 in past, it just adds 1 to that power of 3, right? So I end up with the sum from 0 to infinity, x to the n over 3 to the n plus 1. There's a nice compact form for that function. And what about my bounds this time? So what did I replace x with? X over 3, so I need the absolute value of that to be less than 1, which means I need the absolute value of x to be less than 3, and so my interval is from -3 to 3. Does that make sense? Okay, so that's kind of the basic algebra of tweaking these things. And then, as we saw at the end of the last section, right, you could take derivatives, and as long as you stay inside that radius of convergence, the derivatives work out just fine. So let me just do this. So those first examples from today, right, we're just manipulating things with algebra. We're just plugging stuff in for the x. Now we're going to go back and do derivatives like we did in the last section. So what's the derivative of 1 over 1 minus x? I'll just pull off to the side. 1 minus x is, 1 over 1 minus x is 1 minus x to the negative 1, right? So what's the derivative of that? Negative 1 minus x to the negative 2 times negative 1. So that's 1 over 1 minus x squared. Does that make sense? So the derivative is 1 over 1 minus x squared. And then our rules just said that as long as we stay inside of the interval, right, from negative 1 to 1, the derivative can be found by just taking the derivative term by term. Derivative of 1 is 0. Derivative of x, 1. Derivative of x squared, 2x, 3x squared, 4x cubed, and so on, right? And in particular, then, if we come to this form, the sum from 0 to infinity, it'll be n x to the n minus 1. And what did I say? I wrote down what I didn't want to write down. We usually start this at 1, right, when we take that derivative, because that first term just disappears every time. Now, this isn't wrong, because if you plug 0 and you get 0 here, but if you start taking higher order derivatives, you don't really want to keep it in there. You should always trim off that first term. Does that make sense? And so the theorem in the last section said that you could take derivatives as long as you stayed inside of some open interval, right? So we had an open interval to start with. Our derivative works just fine inside of there. That make sense? So now here's a new series for 1 over 1 minus x squared. What if you wanted a series for, I'm not going to do it, but if we wanted a series for 1 over 1 minus x cubed, what might you do? Right, and it's not quite, right, because this is, what's the derivative of 1 over 1 minus x squared?
1 over 1 minus x.
No, it's actually 2, right? It'd be 2, and then, so this would be 2 over 1 minus x cubed, and so you'd have to put a 1/2 out front. But you can find a series by taking the derivative, and then you just multiply by 1/2, and there's a new series for this guy. We're running a little bit short on time, so I think I'm just going to do one more. But that's the idea. So we can build all kinds of new series by doing this. So last one, find a series for the inverse tangent of x. Okay. Now this, on the surface, might look like, oh, I hated that one. This is going to be tough. But, you'll see it's not too bad. So, when you're asked to do this, eventually this is one that you memorize, the series for this. But, if you're asked to come up with it, you just think about things that you know already, right? We know a series for e to the x, 1 plus x squared, and so on. But e to the x has nothing to do with inverse tangent, right? So we're not going to get there. We know a series for 1 over 1 minus x, and then what's something related to 1 over, or to tangent that we've already dealt with today? 1 over 1 plus x squared. What is that? That's the derivative, right? This is the derivative of inverse tangent. Does that make sense? So now, if we want to build a series for inverse tangent, we're going to take advantage of that. So if derivative of inverse tangent is that, then inverse tangent is the integral, right, of 1 over 1 plus x squared. Does that make sense? And now you just replace the 1 over 1 plus x squared with the series we found earlier. So again, just look it up. I'll just do it. I'm going to do it in, I think I'm just going to do it in the sum form. So, if you don't remember it, that's okay. But the derivative was, it was, right, you replace that x with negative x squared, and so it alternates. So you get a negative 1 to the n, and then you replace the x with x squared, so you should get this. And I'll put parentheses in here for now. Does that make sense? That's just the series for inverse tangent that we found a little while ago. Or sorry, for 1 over 1 plus x squared. All right, and now that big theorem at the end of the last section said that you could let the integral slide past the sum, right? And I'll also mention here, right, this only worked for small x, right, between negative 1 and 1. If you think of, if you remember the, well, let me just leave it at that. So this will only work for those x's. Okay? But the point is, it becomes the sum when you let the integral slide past. Okay? So we integrate both of those, or all of those terms, and what do we end up with? So what happens when you integrate that? Negative 1 to the n will just sit there. What's the integral of x to the 2n? Add 1 to the power, right? And then divide by the new power, right? Just think of integrating any power of x. And that's almost all you have, but then remember we're integrated, and so whenever you integrate, you always have plus some constant, right? And so let's make sure we have the right constant. Most of the time, these are set up where the constant's 0, but you really should check it. And so we know that tangent of 0 is 0, right? So 0 is the inverse tangent. What do I get if I plug 0 into this formula here? Yeah, I should get, right, when n is 0, I get 0. Here, let me just write this out because I'm being a little, I should have written this out anyway. Here, so let me do one more line before I do that. Plug in 0, you get what? X to the x to the 1 over 1, right?
Over 1.
Over 1. Plug in 1, you get negative, right? X to the 3rd over 3. You really, this is fine, you can remember it this way, but it's easier to see when you expand it out, right? So it's going to flip. What's the next term? And it's 2.
X5 over
X
7.
to the 5 over 5
X to the 7th
over 7, and so on, right? You can see it'll do that. And then again, plus some big constant, and again, you can now see why that constant's 0. So 0 is the inverse tangent of 0. If you plug 0 into this, what do you get? You get 0, right? Plus c. I mean, all, it'll be 0, 0, 0. So you just get that plus c. So your c is 0, and so your sum for the inverse tangent is exactly what we came up with. And so we get that, and it's again only defined for those specific values of x because it came from that earlier sum. Is that okay? But the point is you can manipulate either algebraically or with derivatives or integrals known series and come up with series for other functions. So I stopped there. Try the homework from this section. Hopefully that'll get you trying some new things, and I'm sure you'll run into a few problems trying the homework, and so we'll start class next time talking about those. So, all right.